we go also later a bit maybe again to this profiling stuff, but yeah, now we go to basically HTFI, learning how to create files and store some data. And also within HTFI, I can use parallel I/O, which is then useful for speeding up. So basically, this NetCDF here in this application software for weather forecasting, WRF, it is based on HTF5. So this package is called parallel NetCDF. So which really which you can actually what you can see here and what we also will discuss soon is basically by using parallel NetCDF, you really bring down the total runtime of the I/O from here, where it was just regular I/O, down to parallel I/O, which really speeded up by here in this case by more than the magnitude, and then actually one can even speed this up here by what I did here is I used I used a hybrid parallelization using per node 1 MPI task and filled the rest up with OpenMP threads, which means that the numbers of tasks which are doing I/O is reduced. So it's basically then in this case only one per node, and this even speeded also up this parallel I/O. However, this is already these options basically is also implemented in MPI or parallel MPI-IO, where you basically have the where it's basically optional that you can minimize the tasks which are creating files. But okay, we will. Hopefully it becomes clear if we go through the slides. But you basically see the effect. Okay, so this was basically the slide from last time. Basically, I wanted to make also some commercial. We basically can also speed up machine learning applications on our cluster by using Hollerwood and using basically the GPU parts. And this is quite. Hollerwood is quite easy to add to your, if you use PyTorch for your machine learning application to if the bottleneck is really a learning of the training of your networks, then this can be easily parallelized, and then you see basically here in this graph that this is possible to really speed up. To this Hollerwood can enable the scaling, and you can speed up your training of your network. Quite good, and it may be also. This would be maybe also a topic which you can address at their hackathon, and hopefully we have some not success story, maybe success story, some cases like we also discussed. I showed you some scaling plots and so on, which one can also use. The idea would be to write some short stories about this to give you an overview how we can speed up and scale up your applications. And this would be one example. But okay, this is now. Let's go back to the training. Okay, this is a summary of SCORP, what we just discussed the last part. Basically, you have this SCORP wrapper for your compiler. You just write in front of the compiler, and then you can profile your application, which then can visualize with this Cube4 tool. And as I said already, I think there's nice material on this from this COE, from this Center of Excellence on profiling and optimization. So in general, if you need some inspiration or you want to know more of this topic, maybe a good start to take a look to this this website. Okay, now let's take a look. I gave you already some insight what parallel I/O can do if your application is heavily if you use a lot of I/O and which is not parallelized. So let's take a look through it. If my slides are back. Right. Sorry, I just disconnected. I got disconnected from my... Okay, so I'm back. So okay, so in introduction to scientific I/O, yeah, it's basically commonly used by scientific application to achieve goal like storing numerical output from simulations for later analysis. Implementation out of core techniques for application that does not fully fit to memories of the system. So if you have a large use case, you can only access half of your data. So you need to I/O, write and read in only half of it. And maybe what we are basically doing, we're generating configurations using Monte Carlo algorithms. And then we have checkpoints basically after one trajectory, you write out configuration, your status of the application. So this is basically points where you need I/O. And you can basically structure this in parallel manner. You can have different ways to do this I/O. Basically, you can do, the most basic one in an API application is that you just collect all the data which you want to write out on your main process, so on task 0, so send everything to task 0, and then task 0 is writing this out. However, this increased, in this case, you have a large overhead from the communication and from the writing, and maybe even collecting all the data which is distributed over the whole allocation maybe is too large to really store in the memory of the node where task 0 is running. So maybe then you have also to think about how to make this lighter. And so basically there is the possibility to do parallel I/O. Depends a bit on what kind of cluster you are. There's basically a file system hierarchy which supports this, where you have local disks on the node, and then you have a system which collects this right into the storage. However, basically with parallel I/O and MPI, you don't have to. You just need to understand a bit the basics, but you don't have to think about all this hierarchy because this is basically then done by the library itself. Okay, so let's go through this different ideas. So one can write one file per processor, but then one has this option that one writes in a share file that each each MPI task is writing in a file, and then one has this collective shared file where you first of all there are main I/O tasks which first of all collect some of the data, and then only few of these processors are writing to the file. So there are pros and cons for this. So for this file per processor, if each processor is writing, it's the most simple to implement, because you just in your MPI, in your file region, you just open for each processor, depending on your rank, file, and then you write in this file, and then you or vice versa, you open a file and you read data from it. So this is on most of the file systems, it works okay, or it performs well. However, the negative points basically, which are written here, so synchronization of metadata can introduce bottlenecks. and also a large number of files are difficult to manage. So if you, for example, have if your application runs on 1,000 processors or so, you would instantly create 1,000 files, and then even for this number, ls, your usual to list the content of a directory cannot even break for for this 1,000 or 10,000 files. So so it's maybe difficult to manage. So if, for example, if there is a process which doesn't write, or you want things like this, it becomes difficult for the post-processing. And you're not flexible. So if you recognize maybe your application doesn't run so well on 10,000 cores, or maybe your node is out of, you have only, I mean, you need to change the parallelization because of things. This would, I mean, if you want to restart, for example, this would be not possible, because then really the size of the IOs and of the files are linked to the number of tasks which you use to write. Okay, so this would be one option. The other option is really this shared file, that where every task is writing to a shared file. So allows many processors to share a common file handle and simultaneously write to different exclusive regions of this file, each of these processors. And this can be taken on the parallel file system. So this can be taken into account on level of the file system. So you don't have, I mean, if you have this hierarchy that that you run on multiple nodes, maybe each, depending on the file system, maybe each node has an own small storage, and then first of all the process is writing in the storage, and then the system itself is taken care of. You don't have to think too deep to that. The negative points, you can have a significant overhead if regions of a file is used by not only one processor. So if you need to write in a region where maybe 2 or more processors need to write data, then basically you have to synchronize, and this can really impact your performance. This even can happen if you really have exclusive regions. So if you have to synchronize, this shared file writing can have some bottlenecks. The pros basically is that your data management is much better. It's portable. You can start, or maybe a number of files are not depending on your parallelization. So you can start later with a different number of parallelization, or you or you can change the system and so on. And in case of higher formats such as HTFI or NetCDF, it provides some cross-platform compatibility, and yeah. Okay, and then there's a third option, basically, where you really have a shared file with collective buffering. So basically, you not every MPI task is writing to a file, so only maybe a couple. And then first of all, these couple of sub tasks are collecting the data from the MPI tasks which are not writing, and then this couple of MPI tasks are writing to the file. So this improves the performance of the shared file access, because you don't, the synchronization, you don't have to synchronize so much about all the MPI tasks. And indeed, you can also offload some of the coordination work to the file system. So, okay, so let's take a look at basically, first of all, to a library which is very useful for data storage, and which also has the capability of this, which is using parallel MPI-IO to write. Has a capability that one can use this. We'll see later an example. First of all, I will just give you some idea of HTFI. This is so-called, stands for Hierarchical Data Format, version 5. it's a portable I/O library, and it's used for storing scientific data in a database like organization. So the object database data model enables users to focus on high-level concepts like data objects and not on the data structure. Basically, you can you have a root group, and then you can create objects in this HTFI files like groups, subgroups, data sets of various shapes, single value attributes, and you can organize them among groups and data sets. So basically, this is quite nice because it provides a logical view of the file content as a graph. So you are quite flexible to create your own graph, so basically your own file system, and it can be adapted to various use cases. Different. It depends on what kind of data you have. You can adapt basically the data structure accordingly. And it's quite flexible, so you can port it basically to all different systems. So you can open it on a Windows computer or on a Mac or on an Ubuntu computer. And it's basically, because it's independent, the storage system, file system, it's independent of the file system and on the convention. So you don't have to care about binary data structure, if it's big endian or small endian and so on. So how it looks like, so basically, we just go through an example how to create an HTFI file. So basically you can create attributes, data sets, group, and then in this group some data sets and so on. Yeah. So basically you can create directories, and then in these directories you can write data sets that you have a nice structure of your data. And by doing so you don't lose a bit. You basically you can encrypt your information also in the data structure, so that you later, if you look at your files after 5 years or so, that you still be able to understand actually what you write out. If you just write in a binary, then you have to name it properly, the function, the binary name basically, and then maybe you forgot how the data was structured. So the good thing is also that you can write higher dimensional data. You don't have one-dimensional data, which you can set in these data sets. You can also have two-dimensional or four-dimensional data structures. Okay. Okay. Let's take a look to the cluster, I guess. Or are there questions so far? I don't see any. Okay, there are again modules pre-installed on the system. There are a lot of these ones. So the ones which are for HTF5 are basically starting with HTF5. I load here is this version. And then the data structure basically of HTF5 is here we want to create an attribute. So HTF5 comes with a lot of different functions. So basically you can create a file with a function h5 fcreate, then the function name, and then some flags. And then in this function, the function create gives the file create gives you a file handle, and this you can basically use for to write an attribute which is given by here, and then you basically has to close all these attributes again. So basically, this is explained here. So you the function with this function h5 create, you can create an HTFI file in this case in C. You have APIs in principle for a lot of different programming languages, so in Python, or you can open it much and so on. So here it's in this case it's in C. Okay, so basically we already discussed. I mean, the flags are what you want to do with this file. Basically, you can open it with only read, or you can open it by overwriting this file and so on. Okay, let's. I had this. Let's do it. Which file? I forgot again. HTFI. I think in the scratch I had some examples. One. Let's take this one. HTFI, I guess. I think this is now also with a group and so on. So let's take a look to it. Okay. Delete this first of all. Okay, so this is basically what is now here on this file here. I mean, we just create an attribute here. Okay. And this is basically compilation. So what you need basically here is to tell the compiler to use this the library lib htf5.a or .so. Otherwise, it will not compile. So if you don't give the library flag here, you get this error that references are needed. So let's take a look again to the file itself. Basically, you have to include the header of HTF5. By loading the module, you add the include path to your environment variables, which the compiler is looking for. If it's not the case, you can add or you can find out the path by actually what I already said. You can basically take a look where the library is, where the source files or where the files are laying off this module by this module show, and then you get basically the passes which are added to the environment variables. So okay, you just make a show, and then you see that this library is under the build set, this folder. And then you have basically contains all the header files. There's also the definition of this functions. If I find this now, I don't know, HTF5 here. Okay, they're basically HTF5.h is including all the other header files. Okay, and then the libraries are in the lib folder now, usually, so they would be here. And it seems that, well, in this case, I just need there to include this this HTF5 library, and this I'm doing by just telling the compiler minus small l, which stands basically for library, and then this lib goes away. Basically, it looks for then for HTF5 and then this ending SO. If the path is not known, you can add the path with -L and then the path like this. Then it looks into this this folder for the libraries. Okay. Okay, let's run and see what. So I allocate one node. And then just run this. I think I generated x1. So if I just run this, well, it's just serial in this case. I think it will create a file which is called my file h5. I mean, all these HTF5 functions and references can, for example, there's this web page here which contains all necessary information about the available functions. Basically, here in the upper corner, you see this kind of H5 and then the ending. So if you look at for example, here H5F create will be in the folder here. And then you have a list of the available functions, and like here F5F create. You get then a description of what these functions is doing, what kind of input variables you need, and what kind of output it's given to you. So maybe if you use this in a C environment, this might be useful to go through. If you, I mean, you can just use basically available examples, but for an overall view, it might be useful to take a look to this web page. Okay. Okay. Okay, so now what we actually, so we generated now a file which is called myfile.h5, and if you want to go now on and create, basically what we did now is basically we created this attribute here, and now if you want to write a data set, we need to add something more. Basically what is shown here in this example. Let's copy this. This here, and what you see is basically we have now this function h5d write, hd create, and h5s create simple. So yeah, just on the next. So what these functions are basically doing, which h5s create simple, you just create a space handle, which gives information on how many data you want to write. So in this case, this gives you the rank. So what kind of what is the dimension of the data which you want to write? So in this case, you just want to write this data set. It's not written here, but we in the example which I put on my Scratch, I had. It's a one-dimensional. I just for float points number I wanted to write. So then the rank would be one-dimensional, so 1, and then the current dimension would be the size of your application. I think let me copy the file from Scratch because it's always. Do it online, it's always forget to fill out things, and then it's always a mess. So yeah, so basically with this function you give information about the size, what you want to write. There are questions. Okay. Basically, earlier, I use, okay, these files are in my Scratch, so it's in the subfolder which I call NCC. So yeah, so if you basically, if you can, I hope you can access this now. So I have in the NCC, I have this copy folder where just where are the tar file. This is benchmark files, and in HTFI there are these two example files, which is called, one is X1 and one is X2. So we are now working on X1. So you just copy this one if you want to follow. This is, and I go now through the lines of X1. Let's give me. I post the path to the chat, so maybe you can just copy it. And can you confirm if you can copy it, because it wasn't working as you pointed out before. Okay, I think I just will go on. So where I was. Okay, so basically what I wanted to do is, now I want to write, I want to create this data set here. So I want to write a data set to my to the lowest to the root directory, let's say, to the first. For that, I need to give information what I want to write, so how big it is. So here you can basically, here you see I put dimension 1. So I want to write, basically what I want to write is some data. So it's a data array of 4 floats. And then the dimension of this is just 4, because I want to write these 4 numbers. If you have 2-dimensional or 3-dimensional, you would have, then you can indicate this here by increasing the rank to 3 or 2. And then you need to give not only a 1-dimensional pointer to a 1-dimensional array, you need then pointer to a 3-dimensional array where you give the dimension, the size of the 3-dimension of your data sample which you want to write. Then you create a data handle where you basically give the information of what kind of what are the type of the data which you want to write. In this case, I want to write a float, and then these handles are given to the actually write command. So you see you need to give the information what kind of data you want to write, and then which data. So they're basically the pointer to the buffer. And then there are some other options here. Basically, here you can give the third argument here is what kind of transfer options you want to use for providing this data. So this will become, I mean, if you just do a simple I/O, this you can put as default, but in a parallel environment, you will give here the handle for the parallel transfer model, which you will see later. Okay. Okay, let's do this. So let's compile this again. As I said, you don't, the environment path is set, so you don't have to add this to make it not too complicated to have it. allocating a node again, and executed it. So this, as I said, this creates this my file .h5, and now you have basically also options on the badge. I mean, HTFI provides you with some functions which you can use for looking at the data in the bash environment. So basically, this function starts with H5, and then I mean, if you take tab, you get all these options which are starting with S5. What we will here just look at is, I mean, you can also create now data in the bash by using these commands. However, here you just want to take a look what actually is inside this file. So you have this H5ls to really list your data which are in the function. So in this case, let's take a look to my file. So to what these files are looking now. So if you have an HTFI file, you can use this to take a look what kind of data structure this file contains. And in this case, we just write a data set. This group we will discuss very soon, but basically we write out, we created a data set here. And then we can actually take a look to this data set with by setting the path behind the file name. So the path to this data set is, well, the data set itself, its name is dataset 0. So we can just write this behind the file name, and then with -d we get just the output of this data set. So because this data set is, we know it's 4 floats, and you see this is now contained in this under this directory inside this HTFI file. You can copy the whole folder. You can also just copy the file itself. I mean, just executable if you want. I mean, you can also copy the whole folder because the exercise 2 is then basically with the parallel I/O. Okay. So as I said, one can also create groups. And then within this, I mean, to have a better understanding of, okay. To have a better, I mean, to sort better your data. So if you have, I mean, just to have a better overview. And for this, basically this function handle or this function H5G create, this stands for group, which give you a group handle back. And then this you can feed to basically if you this you can feed to your data create. So if you give the group ID, this data set 1 in this case will be written inside this group. And then this basically the same like we did now with data set 0, I can create a data set 1. Okay, so we already did this in this file. I mean, this is just if you look into the exercise 1. This piece of code is just written down afterwards here, basically. So it's already this group is already created in my file. If you take a look to this function, we see that this group is there. And then now to access this in this environment would be just / group 0. Then we see what is inside this folder and this group. There's a data set 1. We can go with data. Right. The problem is tab is not working. So you have to write it off. And then with -d you can take a look what is actually contained in data set 1. This is because we use the same data. It's actually the same like data set 0. Okay, this is just an overview over this exercise. Maybe so you just create a function and then you need to basically to create the space here. This is before you can create the data set, and then you can write this information, the data set information. You can write the data into to this file, and at the end you need to close all the stuff. Okay, so there are also, I mean, as I said, the HTFI is can be used in different programming environments. It's portable to different operation systems. So an example would be Python. There's a Python interface, or in Python there's a module in Python where you can open files and write HTFI files. I guess, for example, you can so what I did is I already installed, I think this is not pre-installed, I already installed it here on this cluster to show you that you can also take a look inside Python to this file structure, and then you can read this out, and you can work on the data, and maybe write it down again into HTFI file to have a better, easier environment like it is now in the C environment, where you really have to do everything, open it by hand and creating the dimension and so on. So this is Python. It's more user-friendly, let's say. Okay, so basically here, so you have to have this this module is called H5PY, and then you can open a file here with h5py.file, and then the file name, and the file name is my file for h5. And then you can take a look to the file itself, this list, and then you see that this file contains of a data set 0 and a group 0, and then actually you can access this group 0 by what I wrote there, the F, and then the pass in this what's called, what's the other name, this kind of apostrophe data set 0, and then maybe you can list also the data elements and so on. So basically you can, this is one option to post-process your data. If you write it in an HTFI file, then you don't know that if you do it on your local computer with Python or and so on. The documentation can, I mean, just look for H5Py module, and then you get an overview over what are the possibilities. I mean, also to create and generate HTFI files in Python. Okay. So are there questions so far? Or remarks? Okay, I think I guess because as I said, there's not so much material left. So of the stuff which I wanted to discuss, I think we can make now a small break, and then we discuss HTF5 or parallel HTF5, and then we can discuss questions and some, I don't know if you have some remarks. You can do this. So I don't know, I would, if it's fine with you, I would just suggest to have a break now, or
you can now if you want, if you finished.
Yeah, no, basically I have now the parallel HTF5, which is again maybe 20 minutes, so maybe we can do this in the last section, because then we have a bit more time.
Okay.
And the question is now if we start at 3 or if we start earlier. I don't know how the schedule is.
Well, if it's only 20 minutes, then let's start at 3. Yeah.
Okay. Or maybe I can. Yeah. Let's start with a. I mean, this is not so much anymore, but we can discuss this in S3. And if there are questions now, I would. Or remarks, or maybe suggestions. I mean, basically, it's also. I mean, as you recognize, it's basically a bit difficult to. I mean, there are a lot of different ways to optimize applications, and it's very individual of the application itself. And really of the use case, it's difficult to address commonly. So maybe if you have things which you wanted to, or which you want to hear in the future, maybe it's a good opportunity to let me know, or to let us know. Or maybe also with respect to programming environments, if it's or if you have interest in a specific more deeper in MPI functions or things like this. I mean,
okay, well, let's take a break for now, I guess.
Yes. Yeah, so I guess, I mean, I'm already more or less in the break. I just wanted to give some, if there is something which,